start quantum mechanics. It will contain a series of lectures on quantum mechanics that will include all the BTEC syllabus and BTEC further. So we will start the first topic of quantum mechanics. Quantum mechanics. As we all know, it's a branch of physics. First, the physics is broadly divided into two parts. The first is called classical mechanics. Classical mechanics. Classical mechanics. Classical mechanics is that physics which is applied on the macro bodies, that's bodies which have larger size. For example, on our celestial bodies, on the planets, on our galaxies and others. And second is quantum mechanics. This is that mechanics which is applied just on atomic size particles. They follow different set of rules, and the bigger particles follow different set of rules. This was invented recently, this quantum mechanics, and this is the earlier branch of physics. This was mainly invented by Newton. It is also called Newtonian physics. Newtonian physics. So in quantum mechanics, what is the basic concept? The basic concept of quantum mechanics is that it is based on probability. Then whatever we do in the world, this is only possible when there is a certain probability in that. For example, if this is a chalk, if somebody says me whether this is a chalk or not, I will say it has a probability of that it is a chalk. I am not sure about it. So anything that involves probability will be defined under this quantum mechanics. So what was the need of quantum mechanics? If the classical mechanics was able to experience all the things that was related to our earth, that was related to our other bodies, that was related to our well-being, whatever we do in our day-to-day life, it also defines the motion of the bodies, then what was the need of quantum mechanics? We will just cover it briefly. What is the need of quantum mechanics? Need of quantum mechanics. Need of quantum mechanics. It's sometimes also called as wave mechanics. It's also called wave mechanics. So what's the need of quantum mechanics? So first of all, we will see some series of experiments. Then after, we will be able to distinguish between the classical and quantum mechanics, and we will then also be able to understand what is the need of quantum mechanics. So let's go to the first experiment. For example, I have a ball. Well, this is a ball, and I made a slit here. The diameter of the slit is equal to the diameter of the ball. Let it be x, and for the diameter of the ball is also x. And here's the screen on the back side. So what I will do classically, for example, if I keep on throwing these balls, either this ball will go through this slit, or this ball will hit here, or this ball will hit here. So what I expect is that here ball will strike right here. For example, if the ball has color on it, this color will get hit on the screen right here, just on here. If I now do one thing, that I take a second ball. I take a second ball. Well, for example, here there's a man who throws this ball, and there's a second man who throws this ball. And I made again one other slit. Let this slit. This slit is also similar to this slit. Now what I will do, if these two men are throwing the balls towards this slits, and the screen will take them. For example, what's the probability here that either this ball will strike here, or this ball will strike here, or this ball will strike here, or the balls will go through the slit and touch the screen right here. So what we expect classically is that we expect that the balls will just hit either here or on the parallel of this slit right here. Just in classical mechanics, we would expect that these two balls will hit either here or here, just because these are particles and they have a different position. These balls are particles. So we need to understand what is a particle. So what is a particle? A particle has a localized position. Whatever has a localized position, that we call it a particle. A particle has a localized position. For example, this charge is a particle. If I try to delocalize it from here to here, so job wouldn't be here, it will be done after here. So for example, this is a duster, I will put it here. At the same time, I will not be able to put the job right there. So if I am going to do that, I will have to remove the dust, then after I will have to put the job. So what is the property of particle? Particle is localized. It is present at one place at one time. This is the property of particle. Particle has second property, that is it has mass. Due to its mass, if we impart any force to this particle, it will get momentum. So particle has a property that it has momentum. The momentum is the product of mass into velocity. Momentum is the product of mass into velocity. So if we impart any force to this particle, it will we will get a momentum because it has mass m, and if we impart a velocity of v, then its momentum will be m into v. Is that clear? So what we are gonna do is we will do same in the wave. What is a wave? First of all, we will learn what is a wave. We will understand the concept of wave. Briefly speaking, a wave is disturbance in any medium. For example, if I am talking right now, I am generating a wave. How I am generating this wave, I will explain a little bit. Sound wave. I am generating a sound wave. So what occurs here is that, for example, here is some kind of speaker who is speaking. As we know, we are speaking and here are many air particles. There are many air particles, and right here there is a listener who listens to this message. Here is a listener. So what I do, the speaker speaks and the listener listens. Actually, what is the speaker doing? He's creating some disturbance in this. For example, this is a particle right here. He just disturbed this particle. But there is a queue of particles. There is a queue of particle here, and they are so closely packed. Up to this, there are particles up to this listener. So what will do? If this disturbs this particle gives a push to this particle and then comes back. Same does this particle. This particle pushes this particle and comes back. This particle pushes this particle and comes back. So they transfer the energy created by the man here. For example, here is a speaker. This speaker gives some energy to this particle, and this particle in return gives the energy to this particle, and this particle, and this energy travels through these particles, and the listener receives energy, which we consider as sound. So literally speaking, that just wave, any disturbance in the medium, or we can say it is the propagation of energy. Any questions?
No, sir.
So wave is disturbance in the medium, and if we disturb any medium, we are creating a wave there. For example, here's a pole. For example, I fix a rope there on it, and on the other hand, I will just hold it right here, and then I will give it a jerk. When I will give a jerk, it will form a wave like this. On the basis of wave velocity and particle velocity, we have two kind of waves: wave velocity and particle velocity. So we first understand what is wave velocity and particle velocity. As I already told you that disturbance in the medium is a wave. So these disturbances are actually created by the particles. So the particles have separate velocity and the wave has separate velocity. Here the particles have velocity of 2 and motion. Their velocity is like this and then back. Here the particle has this velocity. Here the rho particles have this velocity. This particle is going up and then coming back down. So these particles have motion in this plane. For example, if I consider this plane x and y. In this case, the particles have the velocity towards here and here. So they have a velocity in the x plane or in x axis. And in this case, in the second case, the particles have the velocity in y axis. And here it's x axis. On the same now we will consider that this where the wave is traveling. If the particles are right here, this particle are here. Actually, the velocity of the particle is in the x-axis, and in the same time, the wave is also traveling in the same direction. You can see that this particle gives energy to this and this to this, and as I already said that the wave is disturbance in the medium, or we can say wave is the propagation of energy. This energy propagation takes place in this direction. So what I will say that this is a Vp velocity. These particles have Vp velocity. This is a particle velocity. And wave is also moving in the same direction. Let it be V wave or V dash wave. So in the first case, the particle velocity is parallel to the wave velocity. Particle velocity is parallel to the wave velocity. So this kind of wave is called a longitudinal wave. In which particle velocity is parallel to wave velocity. This is called a longitudinal wave. For example, sound wave. Longitudinal wave. Second one. In second, what we see, for example, let it be k second. In k second, what I was saying is that the particles are moving in the y-axis. But as we can see, the energy is traveling in the x-axis. So if energy is traveling in this direction, that means the wave is traveling in this direction. And the particles are moving in y plane, that means y-axis. That means its Vp and it's V dash W. This is wave velocity and this is particle velocity. What is that? Particle velocity and the wave velocity are perpendicular to each other. If particle velocity is perpendicular to wave velocity, this means this wave is a transverse wave. Transverse wave. Transverse wave. Transverse wave. Electromagnetic wave is also a transverse wave. Why is it transverse wave? Because wave velocity. Wave velocity. And the electric field is perpendicular to magnetic field. This, for example, this electric field and magnetic field will be in this way. So electric field will be perpendicular to the magnetic field. So this light is also a transverse wave. So what we have concluded is that a wave in which particle velocity is parallel to wave velocity is called a longitudinal wave, and a wave in which particle velocity is perpendicular to wave velocity, this is called a transverse wave. So what is the property of waves? Well, as you see, the property of particle is the particle is localized, particle has a mass, particle has a momentum equivalent by any velocity. The wave has some properties. For example, the wave has wavelength, it has wavelength, it has frequency. It has frequency nu. It has frequency nu or wavelength is due to lambda. It has frequency. It is an energy actually. It is an energy. So this is the brief introduction of particles and waves. So what is the use of particles and waves in this experiment? As we were doing last week, we were throwing the balls through the slits, and we were getting this. If we quantumly do the same experiment, for example, if we go to the scale of quantum mechanics, that the scale of very minute atoms and particles are to the scale of atoms. For example, we have a laser here. If we have a laser here, and this laser is emitting photons. If we do the same experiment first as we did in the classical mechanics, we'll get a slit here. So wait a minute. So welcome back again. There was an interaction in the video. So as I was studying this, the wave has the property that it is non-localized. I would say unlocalized. As it was told me by a student right now, I just forgot it. The wave has the property of non-localization. What's the non-localization? For example, if I'm speaking right now, this sound goes to this barriers and this. This sound goes to all of them in the class. Whoever is present in the class. So wave has the property of non-localization. The wave is non-localized. So what does that mean? The wave is non-localized means, for example, if I'm creating a sound here, it's kind of wave. If I'm creating a sound, this sound doesn't reach to only a student. This sound reaches to all the students present in the class. For example, if there are 10 boys, my voice reaches all the boys at the same time. So what I'm conveying is that the wave is non-localized. That it isn't present at a particular time. It is present at various. The wave has a property of non-localization. That this wave is non-localized. For example, if I'm creating a sound here, so this sound is reached to all the students at the same time. What I'm trying to convey is that the wave is present at different places at the same time. The particle is present at only one time. At one time, it's only present at one. It's only present at one in the quadrant of space. For example, a particle is right here. It will at time t is equal, for example, 1 second. At the same time, t is equal to 1 second. It can't be present at here. Particle doesn't show this kind of property. So if I have wave, if wave is at t is equal to 1 second, if wave is right here, for example, if wave is here. At the same time, this wave could be present here at the same instant. So this property is called localized. If particles are localized and the waves are not localized. Waves have the property that waves interfere each other. They interfere. Waves show a phenomenon called interference. For example, if I have a chalk here, I can't put the same chalk. I can't add two chalks. For example, there's a chalk, and if I add the chalk here, if I want to add them, they don't form only one chalk. They will still be two chalks. So this is a chalk and this is a chalk. They will still form a separate two chalks. These are two chalks, and they don't interfere. But the scenario in the wave is very different. For example, if this is a wave, some source is generating a wave, and at the same time, and the source is generating a wave. At the same time, if this, for example, t is equal to some instant derivative 1 second, and at the same time t is equal to 1 second, this is S1 source and this is from S2 source. If these two sources are generating waves, for example, this wave and this wave, at the same time, what are these waves? These two waves will interfere. these two is interfere and they will form only one wave. For example, if here is interference have two types, constructive interference and destructive interference. It depends on whether crust falls on crust and trough falls on trough. They will then constructively interfere and they will form a constructive interference like this. They will increase the amplitude of the modern wave. If this was destructive interference means the crust of the one wave falls to trough of the other wave. For example, if this is a wave and this is another wave. As you can see, its crust is trough, the crust falls on trough. This wave will be like this. There will be a destructive interference. As the waves show this phenomenon of interference, the particles don't show this phenomenon. So, what was the goal to study waves and particles is that we will repeat the same experiment that we repeated in classical mechanics. For example, if we have a laser here, this is a laser. It's emitting photons, and we will cap a slit here, one slit. On the back side, we will cap a screen. We'll cap a screen here, this laser, this some kind of slit, and this screen. Either one will expect that this light will get to the slit and hit here on the screen, and get scintillation will be produced, and we will get a glow here. The screen will glow at this spot. The other photons that are striking here and here will not produce any glow on the screen. Till now, the classical mechanics and quantum mechanics are an exact match. As in classical mechanics, what we did, we throw balls to the slit and we got the door at one point on the screen. But in the quantum mechanics, we did the same experiment and we got the same results. Till now, quantum and classical are just matching together. So what is the difference between classical and quantum is that this is the laser, and now I create two slits. This is slit 1, this is slit 2. This is the screen right here. What I expect is that either the photon will go through this slit or the photon will go through this slit, and they will produce scintillations right here and right here. This is my expectation what should happen. But when we experimentally do this, very awkward situation occurs, or very peculiar situation occurs, that is, the scintillations are not produced here, scintillations are produced like this. Like this. What I expect that scintillation should be produced. There is no scintillation, there is just darkness. There is a dark spot, and on here is a bright spot here. And it's maximum bright spot. Maximum bright spot here. That's why it's also called central maximum. Central maximum, because it's the most brightest spot in the screen. So when I did this experiment classically, I just got two spots here and here. But classically, what I got is that I got a pattern of interference. Then there are some sort of waves coming out of the laser. But as we know, the laser emits the photons. Till, for example, when they were Newton, the waves were considered, light was considered as a particle, because Newton gave Newtonian corpuscular theory. Newton's corpuscular theory. Corpuscular theory. In this theory, Newton told that these photons are just like particles. A ball is a particle and these photons are particles. They are, instead of photons, they named them as corpuscles. So this was the wave concept. Now we can say Newton explained light as a particle, that light has a particle nature. But if we consider particle nature here, so this should not happen. But actually we are finding this pattern. So we need another concept to develop. If we consider light as a wave, here, for example, if this is a wave and waves are coming out of this. As we know, it's a wave friends. Waves coming from this. Like this. And this second wave. Second wave is like this. As you can see, these waves are interfering here, and these are producing this spectrum like this. And we will show animation in the video, so be patient and you will come to this concept very keenly. Watch the video with patience and you will know what's the interference pattern, what actually are they doing. So we concluded that the light show interference pattern, and we will conclude that light is a wave. Some phenomena are like photoelectric effect. Photoelectric effect. We will see it in detail. Photoelectric effect. Like Compton effect. Compton effect. These two effects show that light is a particle. They show results that if light behaves as a particle. If we go on the phenomena like dispersion, like interference, etc. The experiment made by Davison and German. What we'll see here, in these experiments, the light behaves as a wave. So what was the light? Was it a wave or was it a particle? There was a nightmare of confusion with this. Is light a particle or is it a wave? So what Einstein did, Einstein said that light is a dual nature. On this photoelectric effect, we got Nobel Prize. Let us start this photoelectric effect with detail. So what the new mechanics is that whatever classical mechanics were not able to explain, we were in a condition that we had to develop a new subject, quantum mechanics, that should explain the other phenomenon. For example, we have the interference pattern that was not explained by the classical mechanics. So we need to develop a new theory called quantum theory. We need to explain the concept of waves. So by the concept of waves, we can easily explain the interference pattern. So this quantum mechanics was evolved by time. So now we will learn about photoelectric effect. What is a photoelectric effect? Actually, the quantum mechanics got started as an experiment. The experiment that I just showed you is actually called the Young's double-slit experiment. Young's double-slit experiment. Young's double-slit experiment. Double-slit experiment. Or it's called the Young's two-slit experiment. The experiment that we just did by now is called Young's double-slit experiment. This gave a blow to classical mechanics, and the quantum mechanics was evolved. So now what we will read is that we will learn about photoelectric effect. What is a photoelectric effect? Photoelectric effect. Photoelectric effect. As we know, all materials in the universe are made up of atoms and particles, and we can say atoms, molecules. And these atoms and molecules are intermade of electrons, protons, neutrons. For example, if we consider any matter here, it consists of many atoms like this. The atoms are not that metallic, I'm showing it. In reality, atoms are very, very small. Like you can't see them even by electron microscope. Atoms are very, very small. For example, this is a piece of matter. This piece of matter contains millions, trillions of electrons. Millions, trillions of electrons in this atom. And in these atoms, the electrons revolving. The valence electrons in the atom are loosely bound. What do? The valence electrons come out of the atom. And there is a positive charge. They leave the atom as positive charge. They create positive charges. These electrons, just here's electron. These electrons just move randomly in the material. But this electron cannot move out the material, because if this wanted to come out the material, for example, this came out the material, and this material will, as a whole, will have positive charge, and this positive charge will attract it back in the metal, and this won't come in the normal circumstances. This electron wouldn't come out of the metal. So what do we do? If we give it energy, if we give some kind of energy, this will come out. So, for example, if we have material and we incident it by light of certain frequency. If we incident some kind of light on the material got irradiated by the incident light, and it emits electrons. This emission of electrons by the incidentation of the radiation is called the photoelectric effect. And the electrons come out due to the incident rays or due to the incident light, and this light may be a visible light, or it may be EM waves, it may be infrared, gamma rays, or whatever. These electrons come out of the metal. This phenomenon is called the photoelectric effect. So, in nutshell, photoelectric effect, what is it? Photoelectric effect is a process. When we, for example, when we incident any light on the material, we should be also suitable material, and suitable light should be material, and the suitable light should be incident on it. When we incident light on the material, the light gives the energy to the electrons, and these electrons come out. And these electrons at that time called photoelectrons. 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 So while if I increase the intensity, of light, what I saw is that these electrons which I just incidented, these come in more and more. And if I increase the intensity in the light, the electrons come out in more number. For example, if I create a graph like this is intensity and this is current. Because I'm actually I'm calculating current here. That's why I'm plotting a graph between current and intensity. This is intensity. Intensity and this is current. What I will see first is that for example, if I keep on increasing the intensity, the light will have some intensity and it will have current at that time. Present current is this and intensity. If intensity is 0, there will be no current because there will be light. If there is no current, there will be light. There will not be any light. So on the intensity, we will plot current here. For example, if we have an intensity of light right here, at that time that current will be here. So graph will start from here. So graph goes on, current increases. It continuously increases on increasing intensity, continuously increasing. So we'll show this graph like this. If there is zero intensity, there is zero current. If there is increasing intensity, the current gets continuously increased. And the second was, what is the effect of frequency on it? Frequency. If we got frequency here and current here. So what we got? On zero frequency, we won't get any current. It's very obvious. On some frequency, we will get current. On a particular frequency, till now up to this frequency, we won't get any current. So when we get current here, for example, if we got current from here, this frequency is called threshold frequency. Threshold frequency. The frequency at which current begins to flow, or at which electrons come out of the matter, is called threshold frequency. If we plot a graph between the frequency and the current, what do we get? We will see that at the threshold frequency, the current will increase on increasing the frequency. After increasing the frequency, the current will just first increase after this time, for example. Then after the current will remain static. It won't move. It will be like this. After this moment, the current will not increase. It will just be static like this. So this is the dependency of intensity on this dependency of current on the intensity, and there is a graph dependency of it on the frequency. So if we are explaining this on the Newton's corpuscular theory, so what I will say that this corpuscular theory will easily explain this. But if we use the quantum theory, so we will just wrap up it. If we use here Newton's corpuscular theory, it will easily explain. But if we use the quantum theory, it will be explained, because in quantum theory we will consider wave as light. We will consider light as a wave. So the wave falls on this. So what's going to, if we increase the intensity, that means we increase the amplitude of the wave. The current should not increase. Logically, the current should not increase because whenever we increase the amplitude, whenever the intensity gets increased, and the intensity has nothing to do with current and nothing to do with the emission of electrons. But if we consider this as a particle, if we consider the light as a particle, then what we'll do that if it has a particle on increasing intensity, actually we are increasing the particles. If we are increasing the particle, that means if there is an electron, it's hit by one particle, and it's hit by one particle, and this electron comes out. At the same time, the second electron, if it is hit by another particle, this comes out. On increasing the particles, these electrons will get more push from other particles and they will come out. So on increasing particles, the more number of electrons will come to the particle. And in this case, if we are increasing the intensity, that means we are increasing the amplitude. That doesn't explain this graph as we have seen the intensity dependency of current on the intensity. If it is the same on the frequency, on increasing frequency, they shouldn't be increasing the current first. They shouldn't be increasing the current, and then it becomes static. Till now. After this, what we will do that classical physics will easily explain this by corpuscular theory. But corpuscular theory says that on increasing frequency, actually vibrating particles very fast. What we are doing there, we have vibrating particles with great amplitude in case of frequency. So what happens that the particle in this will do the push electron, and then at a certain frequency, on increasing the frequency. Actually, the particle is the electron is just moved out of the metal by the particle. In increase of frequency, we are not increasing the number of the particles. We are just increasing the energy. We are increasing the energy of particles. We are not increasing the particles. That is why after a certain limit, we are getting the more current. But after that, when all the particles involved in a wave are consumed by these electrons, by consumed by these electrons, then these electrons come out of the metal at a certain frequency, at this frequency. Then after, there is no increase in current, because there is no particle which will make the electron to come out, because there isn't any particle left which will strike the electron and make the electron come out of the metal. So Newton's corpuscular theory easily explains these two phenomena, these two graphs. But the Huygens wave theory, or we can say quantum mechanics, would not explain this thing. The photoelectric effect says that light is a particle. So light is a particle. So other phenomena like diffraction, interference, others, they showed light as a wave. Einstein discovered this photoelectric effect and concluded that light is particle as well as a wave. For example, if light is absorbed, it's absorbed as a particle, but when it's emitted as a wave. So what we will do, we just studied from here, light has a dual nature. Light has dual nature. That it behaves as a particle and also as a wave. Sometimes it behaves as a particle and it behaves as a wave. So it's absorbed as a particle but emitted as a wave. So light has a dual nature. It's a wave as well as particle. In the second lecture, we will read about the two properties, matter waves and the particle wave duality in all the cases. So goodbye till now. Goodbye till then. Sorry.